Okay, today we're going to take a look at investigating the log curve. Up till this point, you've looked at taking an exponential equation, something like 2 to the power x is equal to 4, and being able to not only solve that by observation, but also take it and rewrite it as its log form. To do that, what we would do is we are always trying to solve for the exponent. So solving for the exponent in this case is x. X is equal to log, the base is 2, it remains the base, and the other number is 4. So being able to move back and forth between exponential and log form is very, very important. Today we're going to focus on what that log curve looks like, and when we use our calculator, why do we get the values we get. We will also take a look at how we transform the function, whether that's up or down, or left or right, or maybe vertical stretches. And we'll do a lot of this through graphing technology, and there is your assignment. So let's get started. The first thing we want to do is we want to explore the log function. Like many functions, we can default back to looking at a table of values. And so I'm going to use our graphing calculator here, and we're going to calculate some values. So the first thing I want to do is I want to find the value of the common log of -1. So on the calculator, I am going to type log and then -1, hit enter, and I get non-real answer. So does not exist. Okay, so we don't have anything when the value of x is -1. What about when x is equal to 0? So let's go back and we'll try that as well. So let's try this again. This time what we want to do is take the log of 0. We hit enter and we get a different error, but it doesn't exist as well. So back to our table of values, and we don't have any values. Let's continue on and start plugging in numbers, and hopefully we will get a solution here. So the common log of 1 divided by 4, or decimal 25. We hit enter and we get our first value. There it is. Let's put it to 2 decimal places. -.60. So -.60, -.60. And I'll just fill in the rest of this table, and then we'll take a look at what our values are. So if you want to pause the video at this point, feel free to do that. Okay, so here's the rest of the table all filled in. The next thing what we want to do is we want to plot these coordinate points onto the grid that we have here. So let's pause once again. Okay, and the points are plotted. Very quick sketch, but we get an idea of what this curve looks like. So let's try and see what this graph looks like here. I'll try and go through many of the points, and we start to see it sort of flattening out there. So here's the graph. We know that whenever we plug in a negative value for x into our equation, we get an unreal answer. So it tells us that there looks like there's a vertical asymptote right at x is equal to 0. It doesn't look like there's any horizontal or vertical restrictions, so range would be everything. And this is the graph of the common log of x. Remember, there is a base 10 here. We don't have to write it in if it's a common log. The next thing we want to take a look at is what happens when we apply transformations. Well, the same thing that applies in all functions. So let's just first of all identify in any function what happens when you add or subtract a number at the very back. And we know that whether if this is a positive number, you are going to have a vertical shift up. And if it's a negative number, you're going to have a vertical shift down. And that doesn't change. And we'll look at some of these examples. If you have a value inside here, don't worry too much about what these letters are, it's more the location. If we have something like x plus 3, for example, inside the brackets, we know that the graph is horizontally shifting, in this case to the left, 3 units. And remember, quick little reminder, this needs to be in factored form, which means if there's a 2 in front, I have to factor the 2 out. And vice versa. If I have a negative sign, you're going to horizontal shift to the right 3 units. The A value out in front is a vertical stretch, again affecting all of the Y values. If it's greater than 1, if it's a fraction or a decimal, then it's a vertical compression. And the K value inside here, again, location is important. This is dealing with horizontal stretches and reflections. And so one way of looking at it is we're always taking 1 divided by K. So if the K value is 2, it's actually a horizontal compression by a factor of 1/2. So if K is equal to 2, like 2x, then we know that there is a horizontal compression by a factor of 1/2. If K is a fraction, then it's a horizontal stretch. And those are similar to what we approached in our polynomials. Let's look at some examples. And one of the best ways to look at these examples is to actually to graph them. So we could graph these by hand, but just for time, I'm going to graph them on our calculator because we need to start using our calculators a little bit more. So using the graphing calculator, I have the graph of log x. I want to sketch underneath it the graph of log x minus 2 minus 5. I'm going to graph these. I'm not sure the window settings I'm on, but there's the first sketch. And the second sketch I don't see right now, so I'm just going to change my window settings back to a standard. And it's probably not going to be the best view, but I'll adjust it as we go through. So there's the first graph of our common log. And then our second graph starts down here. So let's just see if some of that makes sense. So that the -5 should shift our graph down 5 units, and the -2 is going to shift our entire graph to the right 2 units. So I'm just going to change the window settings really quickly here, and I'm going to make, I know there isn't any negative value, so I'm going to maybe make that -1, and I don't even need to go as far as 10, so let's make it go to 5.
Mr. Soden, call extension 221, please. Mr. Soden, call 221.
So continuing on, let's make y min, maybe we only go down to -5, so let's maybe make it, let's keep it at -10, and let's make our y max only go to about 4. We regraph it. This might get us a better view. There's our original graph just going across. Here comes our next graph going here. So it's a little hard to tell on the graphing calculator, but it does look like the vertical asymptote has been shifted 2 units to the right. So that gives us an idea of what our graph is. I'll show you on another graphing software that has the same type of question. So here's our standard graph, y equals log x. That's what we see here. And the next graph is going to be y equals log of x minus 2, and then I'm going to subtract 5. And this gives us a little bit better view. We can see a little bit closer that this asymptote does in fact look like it's at 2. It doesn't actually stop like the graph shows. It goes on forever, but in terms of graphing, it gets so close that it thinks that it doesn't exist anymore. Otherwise, the graph looks fairly similar. There's not a lot of stretches or compressions. It's just a shift down and shift to the right. So moving back to, I'm just going to copy that picture and paste it into our program. Shrink it down just a little bit because it's pretty big. And then what we want to do is just answer some questions about how to find the key features like domain and range, x-intercepts, and we're going to do a lot of this algebraically. So switching back to the equation now, and I'm looking at the equation, I'm looking at domain and range. And if I'm looking at the green graph, which is y equals log x minus 2 minus 5, I see that basically nothing exists in the domain until I get to positive 2. And then from a domain perspective, it looks like I go from 2, not including it, all the way to positive infinity. Range, on the other hand, it looks like it extends all the way down. Even though it doesn't, it does extend all the way down, and then it keeps extending up. So range is going to be everything. So range is quite nice. The x-intercept, we're going to find this algebraically. So we take a look, and it doesn't look like it crosses anywhere close to our numbers. So what we want to do is we want to try and find out where it crosses. And so to find the x-intercept, we want to set y to be 0. And we end up with log of x minus 2 minus 5. I'm going to move that 5 across because this is one big term. I cannot separate this at any time. That's a common mistake. So I end up with 5 is equal to log of x minus 2. Now at this point, it gets a little confusing because we can't just plug this side into our calculator. But when we get stuck, we can remember that this is the common log. And so what I can do is I can rewrite it in exponential form. I'm going to write that down. So when you're stuck, rewrite in exponential. And so it looks like this. 10 to the power 5 is equal to x minus 2. Remember, the base stays the base, goes to the exponent of whatever you're trying to solve, and then whatever's left over goes on the right-hand side. Now 10 to the 5 is a very big number. If we do that on the calculator, we end up with 10 to the power 5, which is 100,000, and then you're going to add 2 to it. So you end up with 100,000 plus 2. So the x-intercept is located at 100,000 and 2 and 0. And when we look back up at our graph that we have, that kind of makes sense because we don't see it anywhere close, and we're already at 20. So it creeps up very, very slowly. The next thing it asks us to find is the y-intercept. And once again, the y-intercept is found by setting x to be 0. So y is equal to log of negative 2 minus 5. Now, some of you don't even need to plug this in your calculator because you recognize that when I take the calculator and I type in log of negative 2, what's going to happen? A non-real answer. And that makes sense from our graph. This graph has a vertical asymptote at 2. So it doesn't look like it's ever going to cross the y-axis, and in fact, it doesn't. So we would say non-real answer, and there is no y-intercept. In some cases there will be, in some cases there won't be. Equation of the asymptote, we have 1, and that asymptote is located at x equals 2. And we can see that shift right here. It shifts that asymptote. And that's how we approach all the questions. So I'm going to sketch another one of these graphs. I'm going to give you some time to try and state the x-intercept and y-intercept, the domain and range, and be able to sketch that graph. If we're doing this by hand, you would actually, or you could possibly use an SRT table. You could use a step method. You could create a table of values based on these numbers that you see right here. Okay, so I've sketched each of the graphs into the graphing calculator, and we can see the first graph right here is our common log of x crossing through 1 and 0. And here is our transformed graph. So let's just see if this makes sense. From the equation, this graph should shift to the left 3 units and have a vertical stretch by a factor of 5. So does it look like this graph has been stretched vertically? Imagine that you're pulling on this end up and pulling on this end down, so making it a little bit more rounded. And it clearly does look like it's been shifted 3 units, 1, 2, 3, and there would be a nice little vertical asymptote located there at x equals negative 3. You would find the x and y-intercept exactly the same way we did in the last question. They're not going to be as big numbers because we can clearly see there is a y-intercept there and there's an x-intercept here. So take a second now and try and find those algebraically. So here is the x and y-intercept. Again, setting y to be 0, solving for x. Notice this step right here. We went from taking the log form to the exponential. So review the last video if you need to take a look at that. Y-intercept is found a little bit easier because it's just a calculation. So if we go back up to our diagram here, this does look like it's just above 2, between 2 and 3, and sure enough, there it is, 2.39, and the x-intercept is located, it looks like at about 2, and sure enough, when we went and found it algebraically, we found it out to be negative 2 and 0. Equation of the asymptote we already stated. Let's look at one last example, and once again I'll pause it and reveal the answer in a moment. Okay, so the first thing that I did is I approached this a little differently. Instead of plugging it into the graphing calculator, I used my transformations. And so I wrote out some of the critical points for the common log of x. So when x is 1, the log of 1 is 0. When x is 10, the common log is 1, and when x is 100, the common log is 2. And I used those points, and I substituted them into this SRT table. So the SRT table, I looked at the original function. I recognize this is a horizontal compression by a half and then a reflection on the x values. So that would reflect it over the y-axis. So here's my value in my SR and T table. And then I also noticed that the y values are going to go up by 4. So I took 1 and I multiplied it by negative a half to get negative 1/2. I then took 0 and I added 4 to it to get 4. And repeated. 10 times negative a half is negative 5. 1 plus 4 is 5. And I continued all the way down. And then I just did a very rough sketch over to the side here. And it's a little tough to see, but basically the negative 1/2 and positive 4 might be somewhere about here. And then negative 5 might be over here, and up to 5 just a little bit. And then finally negative 50 is probably off my page, but to get an idea, I put it here. And so I start to have this line that increases very slowly and continues out to the left, and it continues down to the bottom as far as I can go. So sometimes sketching by transformations by SRT table is just as quick as entering it in the calculator. The remaining parts of this, as you can see, are just solving for x and y intercept. I get an incredibly small x-intercept located very close to the y-axis, and that would be this point right in here somewhere. Again, very hard to tell, but it's going to be really close to the y-axis. And the y-intercept, of course, is undefined because there still is a vertical asymptote at x equals 0. So in this question, I'm going to let you go ahead and try this one. The first step you absolutely need to do is to recognize that you need to factor out the 2 in front. Now that's in factored form, we can see that there still is a horizontal compression by half, but we now have a shift to the right, not of 4, but of 2, because that factored form is there. That's a very common mistake. The rest of the process is very much the same. Once again, these key concepts outline the techniques that we used. There's our translation up, our translations left or right, our vertical stretch or compression, and our horizontal stretch or compression. And there's that 1/k value. And notice these are absolute value signs, which means when you're stretching or compressing, you're doing it by a positive value. If k is less than 0, or if a is less than 0, then you do have that reflection piece, but that's separate. And I'm going to bounce right back up to the top to show you your homework assignment again. Again, page 339, 13579 A and C.